Now we're going to look at simulating randomness. So what is a simulation? A simulation is a collection of things that can happen at random. The most basic event is called a component of the simulation. So for example, if you were flipping a coin, that would be a component. Each component has a set of possible outcomes, one of which will occur at random. So if the component is flipping the coin, an outcome could be heads. A trial is a sequence of events we want to investigate. So a trial could be flipping a coin 5 times. And then after a trial, we record what happened. So it could be, how many heads do we get? That would be our response variable. So in this case, we're going to suppose a cereal manufacturer puts pictures of famous athletes on their cereal boxes. So they put 20% of the boxes have Tiger Woods. 30% have Lance Armstrong. This must have been before the you-know-what. And the rest have a picture of Serena Williams. So we want to make a simulation of how many boxes would we have to buy to get all 3. So first of all, we're going to identify the component to be repeated. And in this case, our component is a selection of a box of cereal. So every purchase of cereal, we get a box. Okay, so how would we model the outcome? In this case, we have the digits from 0 to 9. We have nice percentages. We have 20%, I believe we have 30%, and we have 50%. So that's like 2 out of 10, 3 out of 10, and 5 out of 10. If it had been like 21%, I might need 2 digits to represent that. Do you see what I'm saying? So anyways, we have the digits from 0 to 9 are likely to occur. So we're going to say 2 of the 10 digits will be Tiger Woods. 3 of them will be Lance Armstrong. And the rest, the half of them, will be Serena. Now, if you're going to skip outcomes, be sure to say you are skipping them. So when you're taking the AP test and when I'm grading your papers, I want to make sure that I know what you're going to do with every single possible outcome of digits you get. In this case, we were able to split everything pretty well, so we won't be skipping. The next part, you need to explain how you would simulate the trial. So in this case, this is where we're going to do repeated purchases of boxes. So we're going to pretend to open boxes until we have one of each picture. So we're going to do this by looking at the random numbers until that represents the outcome of getting all 3 pictures. Okay, we could use a random number table or a calculator to simulate. And also, you need to state clearly what you're going to be measuring. Am I going to be measuring how many Serena boxes I get? No. I'm going to actually be measuring how many boxes I have to get all 3 pictures. That's the response variable. So you need to run several trials. The more trials, the better. A usual rule of thumb is 20 trials. And we can later, as we learn more statistics, we'll explain why this works. And for brevity, just right now, that says S, but it should say 5. We're going to run 5 trials. All right. And we're going to use the random number digit list. Digits 0 and 1 are going to represent Tiger. Digits 2, 3, and 4 are going to represent Lance Armstrong. And digits 5 through 9 are going to represent Serena Williams. Each trial will stop when we get all 3 boxes. Okay, so we're going to run 5 trials. So here's my list of random numbers. So the first box is a 7, that's Serena. The next box is a 3, so that would be Lance. And the next box is a 1. Oh, that's Tiger. So after 3 boxes, I got all 3 pictures. I feel very lucky. Okay, so there's trial 1. The next box is a 9. That's Serena. The next box is a 0. That's Tiger. And there's Lance. Wow, I'm really lucky. 3 boxes again. Whoops, wonder why my line didn't show up. There it is. Okay, so there's trial 2 with 3 boxes. Let's start trial 3. The first box is Lance. The next box is Serena. Now we have to go a ways before we get to Tiger. And in fact, we need to get 5 boxes for that trial. So my response variables so far is 3, 3, and 5. Next box is Lance. And then I get another Lance, but I don't need to write that down. I just need 1 Lance. The box after Lance is Serena, and then I get Tiger. Not too bad. 4 boxes, and for some reason it's showing the line. Sorry. Okay, so there's trial 4. So I've gotten first trial, I've gotten 3. Second trial, I've gotten 3. Third trial, I've gotten 5. And this trial, I just got 4. So let's do the last trial. So I get Lance on the first box, Serena on the next box. And it's actually going to take me a while, all the way to the 0 before I get Tiger's box. So that one took me 9 boxes to get. So usually when you're presenting data, you want to be able to show how you got it from the random numbers. And this is one way to model it. And you also, it's nice to do, a little dot plot, basically showing the distribution of data. And so you can see here 2 times it took me 3 boxes, once it took me 4, once it took me 5, and once it took me 9. So that's always good advice. You want to display your data in some way to show people where you got it and what it looks like. Okay, the 6th step is to analyze the response variable. So we want to know how many boxes we might expect to buy to get all 3 cards. Honestly, we've only run 5 trials, so we don't really know at this point. And then you want to state your conclusion. So you could say, we predict that on average you'll need to buy 6 boxes. Now, always state it in the context of the problem. Make sure that I can understand what you're talking about just from the sentence. Don't expect to say 3 and that be the answer. So there's a lot more writing in this class and giving me background and labels and units for your answer. It's not just numbers, okay? So let's look at an example where someone might overstate their case. When I was growing up, they often said that the average family will have 2.4 children. So what's wrong with that statement? That the average family will have 2.4 children. Okay, well, if I averaged all the children over all the families, sure, there were 2.4 children per family, but I dare you to name one family that actually has 2.4 children, okay? So basically, there are 2 things wrong with this statement. One is there are no families that have 2.4 children. Families either have 2 children or 3 children, but not 2.4 children. So usually what you're going to do in this situation is you're going to round up. All right, so you will say that we predict that the family will have 3 children, or probably. Okay, so we need to be a little cautious in our statements. And not only that, we don't say the family will have. We will say it's predicted that the family will have 3 children. See how we say predicted in there instead of saying that for sure they will have it? So that's something you have to be really careful about in statistics. So we're going to look at one more example and show you what a plan might look like. So in this problem, 57 students participated in the lottery for a nice dorm room. Nice triple with a fireplace and a private bath in the tower. Okay. So 20 of the people in the drawing were from the same varsity team. And when all 3 winners were members of the team, the other students cried foul. So we are going to use a simulation to determine whether an all-team outcome is reasonable to be expected if everyone had a fair shot at the room. So the first part is your plan. State the problem, and you're going to identify the important parts of your simulation. So here we have the plan. I'll use a simulation to investigate whether it's unlikely the 3 varsity athletes would get the great room in the dorm if the lottery were fair. Then we have to figure out the components. Well, the component is a selection of a student. Okay. What are the outcomes? How am I going to model it? Okay. Well, I'm going to let 0, 0 to 19 represent the 20 applicants. All right. By the way, normally when we have digits, you're always going to have a 0, 0 situation or a 0 situation. Use that first 0 or 0, 0. Or you need to tell me that you're going to ignore all 0, 0s or zeros. Okay? So it's usually a better strategy when you're setting that first set of digits to include the 0, 0 in the numbers. So the reason we're going 0, 0 to 19, how many different two-digit numbers is that? That's actually 20. Okay, so you're going to usually stop one less than the number you're looking for. We're going to let 20 to 56 represent the other 37 applicants. Okay, so 0 through 19 is 20 applicants. 20 to 56 is the other 37 applicants. And then if we get 57 to 99, we're just going to skip those completely. Now, technically, you could say 01 to 20, and then 21 to 57, and then skip 58 to 99 and comma 0, 0. But then you have to mention another one to skip. So that's why we kind of use 0, 0 as standard. Okay, now we have to define our trial. So each trial is going to consist of figuring out the digits for varsity or non-varsity until 3 people are chosen, all right? And we're going to ignore the numbers we're supposed to skip. And also if we draw the same two set of digits, so if we got 11 and 11, we're going to ignore that, all right? Because we're not supposed to have the same person get, you're never going to get 2 beds in a dorm room. You only need 1, okay? And then the response variable, well, we got to define that. And the response variable is whether or not all selected students are on the varsity team. So that would be a plan for running a simulation. And you could go ahead and try it and see what you think. We have some practice problems here that you're going to answer on your own, and we'll go over it in class. First of all, is a coin flip random? Why or why not, in your opinion? You can kind of ignore those videos that I stuck on the bottom of the lesson. So why do you think, not knowing all the physics and the math, whether a coin flip is random? A casino claims that its electronic video roulette machine is truly random. What should that claim mean? Okay. And then explain why each of the following simulations fails to model the real situation properly. A, use random numbers 2 through 12 to represent the sum of the faces when 2 dice are rolled. So what's going to happen when you roll 2 dice? Is that reasonable? Use a random integer from 0 through 5 to represent the number of boys in a family of 5 children. Simulate a baseball player's performance at bat by letting 0 equal an out, 1 equals single, 2 equal double, and 3 equal triple, and 4 equals a home run. Sounds good to me. Why won't it work? Number 4. A statistics student properly simulated the length of checkout lines in a grocery store and then reported the average length of the line will be 3.2 people. So I think I've given you enough information to answer what's wrong with this conclusion. And finally, you take a quiz with 6 multiple choice questions. After you studied, you estimated that you would have an 80% chance of getting any individual question right. What are your chances of getting them all right? Your simulation should include at least 20 runs, so try that.